All right, let's dive in. Today we're going to explore the pretty wild world of underwater communication. It's a place where our usual tech just doesn't work. We're going to look at a really clever protocol called vector-based forwarding, or VBF for short, and see how simulations help us figure out why it's such a game changer in this crazy environment.
So first things first, you gotta ask, right? Why is this even a problem? I mean, why can't we just use Wi-Fi or our cell phones underwater? What is it about the ocean that makes sending a simple message from one spot to another one of the toughest nuts to crack in all of network engineering?
Well, the short answer is water is just an absolutely brutal place for data. You know, all those radio waves we rely on for everything, Wi-Fi, 5G, they hit the water and just die. They get absorbed almost instantly. So that really only leaves us with one tool that works, sound. And, well, using sound to send data brings its own massive set of headaches.
Okay, so this really breaks down the challenges for us. First up, the big one, propagation delay. Sound moves at about 1,500 meters per second in water. That might sound fast, but hold on. It's about 200,000 times slower than radio waves. That delay is just enormous, and it completely breaks the protocols we're used to. Then you've got barely any bandwidth to work with, tons of packets get lost because of all the noise, and oh yeah, everything is constantly drifting around with the currents. And the cherry on top, these things are running on batteries. Every single bit you transmit has to be worth it.
So, faced with all that, how on earth do you build a network that actually works? You can't use the old rulebook. You have to get creative. You need something that's tough, that sips power, and that isn't built on the idea of a nice, stable connection. And that's where our hero comes in, vector-based forwarding, or VBF.
So, what is VBF? Well, the official definition is a location-based, stateless routing protocol. Let's unpack that. Location-based is pretty simple. It means nodes use their physical position to figure out what to do. But the keyword, the really important one, is stateless. This means that individual sensors don't have to keep track of complicated maps or routing tables of the whole network. And that, right there, is an absolute game changer for saving energy and dealing with nodes that are always on the move.
The key idea behind VBF is actually kind of beautiful in its simplicity. What it does is create a virtual routing pipe that runs from the sender all the way to the receiver. Just imagine an invisible highway cutting through the water. Now, here's the clever part. Only the sensor nodes that are physically located inside this highway are allowed to play the game. If you're outside the pipe, you just keep quiet. So here's the play-by-play. The source node, the one with data to send, figures out the straight line direction to the destination, or the sink. That line becomes the very center of our virtual pipe. So it sends out a packet. Any other node that hears it immediately asks itself two questions. First, am I inside the pipe? If the answer is no, it does nothing, just drops the packet. But if the answer is yes, it asks the question two. How close am I to the center line? The nodes that are closer to that perfect path, they get priority. They're the ones who get to forward the packet next. And this just keeps happening node by node until the packet makes it all the way home to the sink.
Now, this whole approach has some massive upsides. You remember that whole energy problem? VBF attacks that head-on. By not needing to figure out complex routes all the time, it saves a ton of battery. It's also great for dealing with nodes drifting about. But it's not a silver bullet. There's a big F. It all depends on how many nodes you have. If your network is sparse and your virtual pipe happens to pass through an empty patch of water, well, there's no one inside to forward the packet. The message just dies right there. So density is key.
Okay, VBF sounds great on paper, right? But how do you actually test it? How do you figure out the best width for that pipe? You're not going to drop 1,000 sensors in the ocean just to find out. That's where simulation becomes our best friend. And we're going to look at the exact tools for the job. A super powerful simulator called NS3 and a special add-on for it called Aquasim NG.
The easiest way to think about it is like this. NS3 is the main engine. It's this incredible open-source platform that can simulate almost any kind of network you can imagine. Then Aquasim NG is like a specialized upgrade package you plug right in. It's the part that knows all about the weird physics of underwater sound. You know how signals fade, those crazy long delays we talked about, and most importantly, it comes with protocols like VBF already built in.
This diagram gives you a perfect look under the hood. It's all built in layers, kind of like a stack. Down at the very bottom, you've got the channel layer, which is basically the physics engine for how sound moves through water. A step up is the physical layer, which worries about stuff like delays and how much power each transmission uses. Then you've got the MAC layer, which is like the traffic cop deciding who gets to talk. And right up top, the Aquasim routing layer.
See VBF right there? That's the brain of the operation. It's where our protocol lives and makes all those smart forwarding choices.
And we can actually follow a single packet on its journey here. So over on the left, an app on a sender node creates some data. That packet starts its trip down the stack, passing through the routing and MAC layers. Then, boom, it hits the channel, our virtual ocean. The channel does its magic, figuring out all the delays and who can hear what. For any node that receives it, the packet then travels back up the stack on their end. It's a full round-trip simulation, from the moment the data is created to the moment it's delivered.
Okay, that's enough of the high-level stuff. Let's actually get our hands dirty and look at some code. We're going to peek inside a real simulation script. This one is called second.cc, and see how you'd actually build one of these VBF experiments from the ground up.
First things first, you've got to set the rules for your virtual world. So right here, we're telling the simulation to run for 200 seconds. We're dropping 200 sensor nodes into our ocean. They're going to be sending tiny little 40-byte packets, and each one can transmit about 100 meters. Simple as that. This is us basically setting the stage.
Next up, we have to define the physics of our little ocean. This first line, AquaSim range propagation, is a pretty basic model. It just says, if two nodes are within 100 meters of each other, they can communicate. If they're further, they can't. And for the MAC layer, we're using AquaSim Broadcast MAC, which is basically the simplest option. It just means when a node has something to say, it shouts it out and hopes for the best. No complex coordination.
Okay, now this is the important part. This is where we actually turn on VBF. We're telling the helper to use AquaSim VBF, and look at the parameters. We're setting the width of our virtual pipe to 100 meters, and we're setting the target pause, that's our destination, to a specific spot in our simulation. This right here is the code that brings that whole virtual highway concept to life.
Of course, a network needs nodes. This bit of code here, the Uniform Disk Position Allocator, does exactly what it sounds like. It takes our 200 nodes and just scatters them randomly inside a big circle. Now, for this particular run, we're keeping them still, but you could totally swap this out for a mobility model that makes them drift around like they're in a real ocean current.
So we have our ocean and our nodes, but we need them to actually do something. That's where the on-off helper comes in. It's a really good way to mimic how real sensors behave. A node doesn't just transmit constantly, right? It wakes up, sends a burst of data, like a measurement, and then goes back to sleep to save power. That's exactly what this on-off traffic pattern simulates. And finally, the moment of truth. Simulator.run is like hitting the big green Go button. It kicks everything off and runs the simulation for our full 200 seconds. Once it's done, print counter spits out all the juicy results. How many packets made it, how many got lost, and then simulator.destroy just tidies everything up. Simple as that.
Okay, so we've seen the theory, we've even peeked at the code. Let's zoom back out for a second. Why does any of this matter? Why go through all the trouble of setting up these simulations just to watch little virtual packets swim around?
Let's boil it all down. VBF is a really smart protocol that uses location, not complicated maps, to get the job done. That whole virtual pipe idea is brilliant because it stops tons of nodes from transmitting when they don't need to, and that saves a massive amount of battery. And here's the kicker. Tools like NS3 and AquaSim are not just nice to have, they are absolutely essential. They let us test everything, find the bugs, and perfect the system in the computer before we spend a dime on real hardware.
And you know, the source material puts it perfectly. It says this whole setup offers a practical way to study VBF behavior under realistic underwater conditions. And that's exactly it. It's the bridge that takes an idea from a whiteboard and turns it into something that could actually work, something that could be collecting vital data from the bottom of the ocean. And that leaves us with one final question to chew on. In our little experiment, we set that pipe width to 100 meters. But what if we doubled it? What if we made it 200 meters wide? On one hand, a wider pipe means more nodes are eligible to help out, which could improve reliability, right? But on the other hand, more nodes talking could just lead to more chaos and collisions, making things worse. Which one is it? Well, that is exactly the kind of question these simulations are built to answer.